Okay, hello, everybody. This is Mr. Fasoni. We're going to be continuing the 6.3 lecture. I'm going to dial it or rewind it a little bit back to the beginning of concept 1.b about common and natural logarithms. Some of the classes we got through this, some we just barely touched on it. I just want to bring everybody back into sync with one another. So a common logarithm is when we have a logarithm that is specifically base 10. And we denote it as log base 10, like this, or simply by just the word log. We call it a common logarithm because it's used to measure things that we kind of see that we've assigned value to, I guess I should say. Like, for instance, if you want to compare distances in the solar system, these are massive distances. So instead of having a diagram where you've got, the sun and then the inner planets and then, Jupiter and Saturn way out there and things like that, you run out of space if you keep it on an equal scale the whole way through. So you could actually depict it using a common logarithmic scale, which means that every distance of whatever value it is 10 times the distance. So it keeps the values closer together as we move forward. It's a little bit different to think about, but it's a way to kind of compress the scale while still giving information. So anything that we measure using the base 10 number system, salary information, population information, distances, things where orders of magnitude matter. So that's log 10, and we just denote it by the word log. Oops, the word log. And then we also have the natural logarithm, which is the same idea except with the base e. And we denote that by log base e, but usually when we talk about it, we use the letters ln. And I believe this is from French or Latin. It stands for like log natural, something like that. That's the natural logarithm. We have all the conversions down here as well. But the natural logarithm is stuff that naturally occurs in nature. The reproductive rates of animals, the spread of a bacteria sample, things like that. So things that appear in nature, we use the natural logarithm. Things that we've assigned values to, that humans have assigned values to, like distances and magnitudes of things, or things that we've created like money, we use the common logarithm typically. So the nice thing about this is that both of these values or both of these functions appear on your calculator. So even the Windows calculator that's built in has both a log button and a natural log button. So if I want to calculate something, if I want to calculate the natural log of 45, I just hit 45 and then click the ln key, and I get the natural log of 45 is 3.8. All right, let's continue forward. We'll do a couple of evaluations. I just gave an example on this, but if we wanted to find the log of 21 and then the natural log of 54 using a calculator and then round to 3 decimal places, it is very straightforward. All I have to do is type in 21, hit my log button, and it tells me that the log base 10, or the common log of 21, is 1.3222 blah, 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 blah. If I wanted to round that out for log 21, it would give me 1.322. So in other words, 10 to the 1.322 power should approximately equal 21. That's all that's saying. All right, similarly with 0.54, if I want to find the natural log of that, I just type 0.54, hit the LM button, and I get 0.616, negative 0.616. So the natural log of 0.54 is equal to negative 0.616. That's rounded to the 3 decimal places. And again, that's just saying that e to the negative 0.616 power would be approximately equal to 0.54. So there's not a lot of use with this just yet. We just want to get used to using the calculators for that. But in a later section, we'll be doing what's called a change of base, or maybe we'll be calculating something strange, like maybe, I don't know, log base 4 of 13. So I want to know what power of 4 will give me 13. And I can use some of my logarithm values or logarithm functions on my calculator to help me calculate these things. But we're not there yet, so don't worry about this just yet. All right, let's continue along. I think this is the last concept for the section. Oh, no, there's two more. This one is called inverse properties of logarithms and exponentials. So the logarithmic function and exponential function are defined to be inverses of each other. And like we say with inverses, in other words, we can use one to undo the other, leaving the value x. So similarly with addition and subtraction, if I add 5 to something, I can then subtract 5 from that total, and it will take me back to my original value. So x plus 5 equals something, and then I subtract 5 from that something, and it takes me back to x. Same with multiplication and division, and now with exponential and logarithmic functions. So if we've got two functions, one defined as g of x, this is just a name, we're just calling it g of x right now. Let's say the logarithm function is called g of x, and it's log base b of x. And then the exponential function we're calling f, again, it's just a name. We're saying f of x is equal to b to the x power. Then we have these two, what we call compositions of functions, where if I put one function as the input of the other function, we end up getting this nice cancellation. So let me try to kind of write this out, because this is a lot of crazy notation. So we'll start with the left side one. It says g of f of x. So f of x is the inner function. I'm inputting x into f. I'm calculating it. And then whatever that gives me, I'm going to put that into g and input it again. So let's do this step by step. We've got this equivalence here, but I don't think it's really making a lot of sense. So what I'm saying is, if I take f of x, we know that f of x is equal to b of x. So then I'm going to take g of f of x, or in other words, g of b to the x. And then I'm going to run that through my function. Well, whenever I input an x into g, I'm going to put it into this logarithm function. So it becomes log base b of b to the x power. Well, the nice thing about this is if these bases match, if the base is used in the y value of our logarithm, remember this value here, this b of x is typically our y value when we're thinking about a standard logarithm. Let me write that above here. Remember, we usually talked about this log base b of y is equal to x. That's generally how we thought about it. So if my y value is a power of b, well, we can just get rid of the b's and keep the power. So let me show you what that means with an example here. So let's say I've got log base 2 of 2 to the 4th power. Well, this is just the same as log base 2 of 16. So it's saying what power of 2 will give me 16? Or in other words, what power of 2 will give me 2 to the 4th? Well, in both of these cases, it's 4. I evaluated 2 to the 4th here on the bottom, but I don't have to do that. I can just take that exponent and put it on the right side of the equation. Log base 2 and the 2 in the y value, the 2 to the x that's in that y value, they both go away. So we end up getting the inverse. Or, I'm sorry, we use the inverse functions to revert back to x. So don't let this notation mess with you. It's just we're evaluating the inside function first, and then whatever that gives us, we're going to take that thing. In this case, the thing in question is b to the x. We're going to put that right inside the second function, the outer function, evaluate that through, and then we're going to use our properties of logarithms to get back to x. All right, let's try this with the other listing here. Let's see if I can fit it in here. So I've got f of g of x. Remember, we read this from outside in, right? So f of g of x. So I input x into g. Remember, my g function is just log base b of x. So I'm going g of x, well, that's just going to be equal to log base b of x. And then that means I'm going to then take that g of x and I'm going to put it inside of the f of x. That means that f of x is going to equal b to the power of log base b of x. There's a lot of stuff going on inside the exponent. Clear myself some working space. I'm going to expand this out a little bit. F of x is equal to b to the log base b of x power. Okay. So again, we're trying to figure out what this is going to be. According to our notes here, it shows that it's going to be equal to x. But we want to show how it cancels out. So again, I'm going to just look at powers of 2. So if I, for example, have, and actually I'm not even going to write the f of x stuff. If I just have 2 to the log base 2 of 16, well, I can evaluate the stuff up here in the power. Log base 2 of 16, that's going to be equal to 2 to the, well, log base 2 of 16 is just 4. 2 to the 4th gives me 16 again. And this will work for any power. We just need to know how to evaluate it. So if I have something like this, f of x equals b to the log base b of x, then what ends up happening is these things cancel and I just get x at the end. So this is a tool that we can use to simplify things if we're trying to solve for an x that's maybe up in the exponent, or solve for an x that's in the logarithm. We can use these inverse functions to kind of clean up stuff and get rid of things in our attempts to solve stuff. But right now, we're just going to get used to using them. So if I want to simplify this, 10 to the log 18 and then log base 4 of 16 to the x. Well, let's just go through these. Don't let this mess you up. This is just 10 to the log of 18. Well, what did we just learn about? With these logarithms, if there's nothing written right here for the base, that means technically it's base 10. It's common log. You could write that in to help you. And then at this point, all you're doing is you're canceling stuff. You're left with 18. Next one's got a little bit of a trick to it. Let's say I'm converting from a logarithm, log base 4 of 16 to the x. Okay, so this is a little bit funny, but not too crazy. The key here is just to understand the relationship between 4 and 16. These aren't the same number just yet. But can I rewrite 16 as a power of 4? Well, yes, I can, right? 16 is just 4 to the second power. So if I rewrite that 16, now I've got log base 4 of 4 to the second power to the x power. I can do some manipulation with those exponents. And I end up with, I'm going to go up here, I'm going to end up with log base 4, 4 squared to the x power, 4 to the second to the x. Remember, power of a power rule, that just becomes 4 to the 2x power. I'm putting parentheses to show that separation. And then from here, I'm ready to go. I've got my base b showing up both where the actual base is and then also as part of my y value of my logarithm. So I can cancel both of these. And what I get at the end is just 2x. The tough part here is just recognizing the relationship between the actual base and the number that's inside that, what we call the y value, the value that's being looked at for the logarithm. Remember, a logarithm is just a question. Log base 4 of 16 to the x power is saying, what power of 4 will give me 16 to the x power? That's all it's saying. All right. So that's inverses. And then finally, we have a little tiny bit about the graphs of natural base functions. So this is just to give you guys some visibility on this. We'll mess with the graphs a little bit in 6.4. Mainly the transformations of functions where we're translating, reflecting, or stretching and shrinking the functions based on what we're doing to the equation. But for right now, the main thing to know is that these graphs are inverses of each other, and because they're inverses of each other, exponentials and logarithmic functions, they're going to be reflected over the line x equals y. Any function that's graphed with its inverse will be a mirror image of the inverse mirrored over that line x equals y. So our first one we're looking at is b to the x power. This is a exponential growth function. So that's a growth function. So it's starting low and then rapidly rising as we move to the right. And as you can see, if we reflect that, all of our x coordinates become y's, all of our y coordinates become x's. So 0, 1 is reflected at 1, 0. And then this asymptote over here on the left that approaches the x-axis is reflected and becomes an asymptote that gets very close to the y-axis. And then this rapid rise on the left side on the exponential graph, when reflected for the logarithmic graph, instead of becoming a rapid rise, it's moving rapidly to the right forever. Still going to grow, but it's going to move to the right faster and faster and faster. Similarly, with a decay function, like this one here, we've got some kind of value that's causing it to go downhill. Our x values between, or I'm sorry, our base value is between 0 and 1. So as our x grows, we are decaying as we move from the left to the right. We're going downhill, eventually hitting that or getting close to that asymptote. As x gets larger and larger, the y values get smaller and smaller towards 0. But again, you can see those reflections are happening. At 0, 1 on our blue graph, it gets reflected to 1, 0. The only difference here is that on the first graph, everything was on one side or the other of the reflection line, x equals y. On the decay graphs, we have both graphs crossing the line x equals y, so it gets a little bit more confusing as to what's happening. But again, we can reflect every single point. I'll use some orange here just to show, we've got 0, 1 and 1, 0. Those are reflected right across the line x equals y. If I pick a random point, let's say right here, I can find another point around here, and I can connect those and show that they're reflected right across at x equals y. That was not a very straight line. Let's see if I can maybe turn on my line function. And we see that it's reflected right across. And this works for any value we want. I can pick a value here and it will reflect to another value on the other side of the function, or the other side of the line of reflection. All right. So that's it. There is a note here at the bottom. Again, it's just what I've already kind of talked about. Note that the y-axis is a vertical asymptote of the graph. F of x equals log base b of x. That's the reflection of the horizontal asymptote that is on the x-axis for the exponential functions. And then the domain of f of x equals log base b of x is larger than 0. So remember, on exponential growth and decay functions, the domain was all x values and the range were all y values greater than 0. These domains and ranges have swapped places on the inverse functions. So now my x values are all values bigger than 0, but my range is all real numbers. I can have any y value I want, but only positive x values. All right. So that's it for chapter 6.3. In the next class, we'll be going forward with 6.4 for the lecture, but there will be a 6.3 problem video that I'll be putting out shortly after this as well. All right, guys, have a good day. See you in class.